Welcome to my Lab 3 video for Physics 2211. So the purpose of this experiment in part 1 was to use GlowScript as a computational model to simulate gravitational forces between a star and a black hole, and then calculate the mass of the black hole. And then part 2 was to use that mass of the black hole to calculate a safe initial velocity of a spaceship so that the ship comes close to the planet without leaving the system, entering the black hole, or crashing. Just a preview of my results is that the mass of the black hole and my initial velocity, and both are shown right there, and I'll talk about that later in the video. So some introduction to key concepts. So from prior chapters, we learned about Newton's second law, which is that F net equals the change in momentum over the change in time. And then this equation can then be rewritten to the velocity update formula, and that can be rewritten into the position update formula. And these two will become very important later in the video when we start making our code. And then also we will talk about the universal law of gravitation, and that can be used for our net force components. And our net force components is something that we learned this chapter can be divided into our parallel and our perpendicular components. And in our p hat or parallel, that offers a change in speed, while n hat or perpendicular is change in direction. And for this experiment, the equations for the net forces will look like this. So an introduction and free body diagram. So on the left, we have part 1, which is the system being the star and the surrounding speeds, the space and the black hole. So we have two objects basically, and we have a force in between them. And the only force is going to be gravitational force. And then in part 2, we have the star and the planet being the system, and the surroundings be the space and the black hole. So now we have three objects, and the free body diagram looks like that. So before I get started, I just want to talk about the reasonings and assumptions. Because because we're in space, the only forces that are acting on these objects is going to be the gravitational forces, and F net is then going to simply just be the sum of these gravitational forces. And then because universal gravitation is a non-constant force, the average velocity can be substituted for final velocity. And then, as I said, changes in parallel forces is the change in force magnitude, while the change in perpendicular force is the change in force direction. So as initial conditions, these are kind of given. So the star mass and then the delta T is seconds in a day. And then these is my iteration for part 1. So we have momentums equals mass times velocity, and then we have our change in velocity and our change in momentum, and we just have our F net like talked about before. So all this is getting compiled into a code, which will evolve into part 2. Then we have we can solve for the mass of the black hole using this equation, and that gives us when I run the code, we get this. So I had this planet basically orbit around this black hole, and these arrows represent the forces that is being exerted on the planet. And we found that the mass of the black hole is 1.227 times 10 to the power of 34 kilograms. So now in part 2, we have our initial conditions of the don't crash. So we had the mass of the black hole, which I found in part 1. That becomes an initial condition. And then we guess and check these initial speeds of the planet, because we want to find a safe initial velocity, basically. So then basically we sum all of the net forces in all these different parts. So we have the Fg on the planet from the black hole, Fg on the planet from the ship, and then F net on the planet is just the sum of those two. And we do the same thing on the ship. And that's just using the universal gravitation equation. And then we have our velocity update formula and our position update formula that I talked about prior. And then all these are ran, and we get something that looks like this. So as you can see, our spaceship comes close to the black hole, but then it doesn't fall into the black hole, and it then gets pushed away. So the initial velocity that works is negative 2.8 times 10 to the 7 in the x direction, and 5.5 times 10 to the 8 in the y direction, meters per second. And the ship is now 9.093 times 10 to the 9th power meters away. So some errors could result in issues in coding, and that could impact the initial velocity as well as the average mass calculations. And then the code in GlowScript could have errors, and the guess and check for initial velocity could obviously be flawed. So what does it mean? So how does the net force and its parallel and perpendicular components differ from the rate of change in momentum and its parallel and perpendicular components? So F par and F per are just components of the net force that correspond to the motion of an object and the direction of its forces. So the net force and change in momentum are calculated in different ways, since the net force requires both masses and the distance, while the change in momentum only needs the mass and velocity. So in summary, the significance difference is that F net requires the mass of the black hole, while the change in momentum does not. And then finally, for the what if, what initial velocity would your spaceship need in order to enter some kind of orbit around the black hole? The initial velocity would have to be greater than the gravity of the planet, but smaller than the gravity of the black hole. So we have to find that kind of medium spot. So I couldn't really figure it out, but just by guessing and checking, this is a model that I